All right. Let's see. Make sure everything's correct. Can everyone see my screen? Perfect. I'm going to take that as a yes.
I can see your screen.
Great. Right. So hello, everyone. Yeah, as was mentioned, I'm Simon. Nice to be here. Today, I thought I would go over some code that started out as purely some scripts that I had lying around a couple of years ago for meshing, primarily from polygonal structures, which is what we're interested when you work with GDS. Over the years, so it's a cycle of you need to. So I'm not really a software engineer. Like Chloe said, I'm from the hardware world, and so in the hardware world, we usually get a script working, and then get some numbers out of it to do our research or our R&D development. And then, but over time, as things became more and more useful in those scripts, I would formalize them inside this package I call Meshwell here. And so if you want to follow along, I just redid the docs last weekend for this talk. So that's what I'm going to be going through today. So if you want to follow along, I'll try to paste I will paste the link to the repo in the chat. And so, yeah, it's basically just the docs here. And the plan is for me to, so Meshwell, what is Meshwell? It's, like I said, it's this slight formalization of these scripts that I found useful to mesh polygon type structures in 3D and 2D. It's a wrapper around GMesh, and GMesh is the number one, I would say, open source, mesh generating software. If you're using any sort of open source solver, to FEM, TCAD, whatever that's open source, they usually have support for GMesh, so it's a good tool to know. So yeah, let's just get started. If you have any questions at any point, just feel free to interject. Just chime in, and we can.
On Zoom?
Yeah.
Hmm.
Great. So, sorry, is there a question already, or?
Yeah.
Okay. All right, so to start with GMesh, like I said, GMesh is this software that's created by two professors in Europe for meshing. It's a very powerful tool. So first, I'm going to just quickly go over the Python API for GMesh, show you what's good about it, what's bad about it, and why we created Meshwell. So in this notebook here, I'm just starting by doing my imports, and then I will first generate a geometry. The canonical way of defining a mesh in GMesh is to do it the so-called bottom-up way. So what is that? As you can see on my code, can anyone see? Let me sure everyone can see the code well. I'm not seeing what I'm sharing, so hopefully it's clear. It's clear. The canonical way of defining a geometry in GMesh is to first you create a model. The model is what holds your CAD entities and your meshes. And then you start by adding points. So here what I'm doing is I'm simply defining points from, I'm making these calls to the CAD engine and saying I want the point at 0, 0, 0, one at 2, 0, 0, one at 2, 1, blah, blah, blah. Oops, just then from these points, you create lines. From the lines, you create closed loops. From the closed loops, you create surfaces. And then if you want a 2D mesh, then you can stop there and you just generate the mesh in 2D. So let's see what that looks like. Whoops, imports. And so once you run this, you get a bunch of output. Not too much here. We can go over it later. And now that you have a mesh, you usually want to look at it somehow. And the recommended way to do that is to actually run the GMesh GUI. So in my documentations, I spent some time finding a way to actually render the meshes in the browser here in an interactive way using Plotly. That's pretty nice, but that's pretty slow if you have very big meshes. So I would recommend you running, you can actually run the GUI directly from these calls here. So I'm just going to run this. On my second screen here, let me pull it on the first screen, the GMesh GUI ran. So what I'm showing here is a XAO file. That's a file format for CAD. So CAD it's not the mesh, it's these points, these lines, these surfaces that I was telling you about. So just a representation of these things. So what we're seeing here is the point at 0, 0, 0, as you can see, then the point at 2, 0, 0, and so on, forming this polygon. You can see the points are labeled with integers. So it says 0.1 here, and then 0.2, 0.3. And if we had actually stopped and looked at the, let me go back to, yeah, if we had stopped and looked at the output of these, what these API calls return, you would see they're all integers. So everything in GMesh exists as an integer. It's usually an integer pair of, the tag of the entity you created and its dimension. So here points would be 0, dimension 0, line 1, surfaces 2, etc. And then if I hover over the lines, you can see you got the same thing here of line 3, line 4. Again, they're labeled by integers. The lines do have boundary points. And we're not going to see much more because GMesh is not really meant to look at the CAD. So what we should do now is look at the mesh that was generated. So that's the next line. And here the colors are absolutely terrible. Let me see if I can change that. It's a bit out. Yeah, there we go. Actually, it would be here in options somewhere. The menus are really bad. So let me see if I can change the color of the mesh. Color, the surface. Groups. Let's move on. Let's make it, very dark. There we go. So here you can see the same CAD model that we had before, except now we actually have a tessellation. And as you can see, the tessellation does respect the points we had. So wherever we had explicitly put points, you'll also get a mesh node there. Everywhere else, though, what we use is called an unstructured meshing algorithm, which means that from the CAD basically the surface we define using the points and the line of the surface, GMesh then goes ahead and figures out where to place node points to get these roughly, good-looking triangles. I say roughly because it's not always the case. So that's the first example, just doing a very simple mesh. And again, I said I came up with a way to render this in the Python notebook directly, which is nice. And here you can see I'm also coloring different dimensions differently. We'll get to that. We'll get to that soon. So it would be extremely annoying to always have to create a mesh, from points and lines and then closed loops and surfaces. And if you go to 3D, you can imagine it gets even worse because you have to assemble the surfaces into a closed shell, and then that defines your volume. It's really painful. And so there are some built-in primitives inside GMesh that you can just call directly. And so they just exist. Indeed, you can directly do API calls, for instance. So instead of doing a rectangle by points, lines, surfaces, you can just call, the rectangle function with some parameters. Here you can see it takes, an X position, Y position, Z position, and then dx, dy, and then just gives you a rectangle. Same thing for more complicated shapes, a disk, very circular disk. So let's just run this for a second. Same kind of output. Here, I'm not going to pull up the GMesh GUI, but you can imagine that it looks similar. So here I define the rectangle, origin 0 with a size 1. So I have rectangle origin 0, size 1. And then a circle at x center 3, well, center 3, 0, and then radius 0.5. So that's what we're getting. So that's all good. But it's also still limiting because there's only a very limited set of primitives you can call upon. And so the next thing you can do is constructive geometry operations. And that's where the good stuff really begins. So constructive geometry is just Booleans, right? So what if I have two simple shapes and I want to take their difference or their sum or their intersection? So you can do that as well. So here, if we start from the same rectangle, the same circle, we can, well, maybe translate it so they overlap. And then what I'm going to do is I'm going to take the difference of the two using this cut operation. So let's run that. Again, output. Let's look at the mesh. So here I made sure they were overlapping. So I actually centered my rectangle, centered my circle, and then I took the difference of the box and the circle. And as you can see, I now have a rectangle with a hole in it. So again, that's fine. But so far we've only dealt with pure meshes in the sense that I define this box, I define this circle. Within the model, they exist as integers. And more often than when you're doing simulation, you're not necessarily interested in the specific entities, but more in collections of entities, right? So if I'm simulating a chip and I have a lot of, you can imagine I have a lot of silicon, for instance, I don't want to have to remember every single piece of silicon on my chip. I want to be able to call the collection of silicon, and in my simulator just say, oh, silicon assigned this epsilon or assigned this conductivity. And so in GMesh, the way to do that is called physical entities. And so it's relatively simple. After you define your entities like we did before, here I'm creating 2 rectangles and 2 circles. What you can do is you can take the tags associated with the entities. So remember, everything's an integer. And you can create a physical group with a string name. So let's do that. Let's render that. And here I'm actually going to have to be more careful. So here what I've done is I did my mesh with the boxes and the circles. But afterwards, I added these physical groups. And now the way I'm plotting it is I'm coloring them by physical group. So now as you can see, my 2 rectangles, they're both blue, and they're labeled in the mesh, they are tagged as. Sorry, question? Oh, yeah. So in the mesh, in the GMesh output file, .msh file, there is an association now between the name boxes and there's an integer tag that then gets propagated to the entity. So these 2 rectangles now have another integer that says, oh, we're boxes. Same thing with the circles. They're now circles. So that's nice. If you've noticed so far, I've been very careful not to overlap things too much. And the reason is that if you just create 2 rectangles and overlay with each other, there's no concept of, oh, the mesh should be, the mesh between the 2 rectangles should be the same. GMesh will literally look at each rectangle separately and say, okay, they both get meshed separately, because the way it does the meshing is it starts by meshing the lines, and then it meshes the surfaces defined by closed lines, then it meshes the volumes defined by closed shells of surfaces. And if things overlap, it doesn't know about that. And so that's the first pain point that I'm that highlighted and marked down here. If things are overlapped, the meshes are not connected. And in simulation, you don't want that usually. You want one seamless mesh that characterizes your system. The more important problem is that, everything's an integer inside there. So if you start to, heal the mesh, take different rectangles, and make sure that they don't overlap, that you have everything cataloged nicely, then you start adding a lot of extra entities to do that. And that's a lot of integers to keep track of. And that's very painful. And so basically the package, the scripts that I created in this package, they deal with that problem. So if I move on to my next notebook here, we first overload some of these primitives from GMesh. And the first one that I did this for, I called the polysurface. And so what it does is that, it can take a, it's no module name shape, we go great. Let me fix my environment quick. Make sure we have everything. All right. All right, great. So hopefully, I don't know if you guys know the library. So the 2 problems, different entities don't mesh well when you overlap them. And also there's lots of integers to keep track of. There's no concept of a polygon. So the first problem we're going to fix is we're going to add a polygon object to GMesh. And the way we're going to parameterize the polygon is using the library Shapely. So I don't know if you guys are familiar with Shapely. It's a very popular geometry manipulation library. It has very convenient utilities to deal with polygons. And so first, I'm going to create a Shapely polygon with a hole, and then another Shapely polygon, and I'm going to combine them in a Shapely multi-polygon. And I'm going to show you that. So the polygons look like this. Basically, I just made two boxes and one as a hole here. And what we're going to do is that now we have an overloaded GMesh model, and we have a new object called the Polysurface that takes in polygons, takes in a model, takes in a name for this physical tags, and then when we mesh it, it'll just work, as you can see. So let's take a look. So this is the GMesh output like before. As you can see, a few things happened. So this is here, I'm just coloring the mesh, so we don't see the actual mesh, but we can see the rectangles. So if we go up the Shapely, using Matplotlib, I could plot my Shapely polygons like this. And as we can see, they get rendered in GMesh and with holes and everything. And also they get appropriately named. And the way they are named is this polysurface had a physical name. So if you look in the surface, that's the name it's going to have. But also the interfaces between the different entities also get a name. Here, my polysurface one gets a boundary with none because there's nothing else. So it's the outside of your simulation. But in the more complex examples later, we'll see it's actually very powerful. And Shapely is a very powerful library. You can make, for instance, there's very simple ways to make very complex polygons. So here what I'm doing is I'm taking, a box polygon. I'm defining two lines using this line string object. I'm buffering the lines, which means I'm taking them from a 1D string and I'm creating a polygon out of it. So that's the pill-looking shape you can see here. And then I'm going to take the difference between the hole and these two pills. And I can just take that Shapely polygon, give it to my polysurface, and GMesh is just going to run and give me, the associated mesh. We can even show the wireframe to see that, points get placed, lines get placed between the points, and so on. So that's the first problem Meshwell solves. It allows you to, it basically adds a, polygon meshing to GMesh. That's relatively straightforward. What's a little less straightforward is doing this in 3D. So in 3D, what we're interested in is taking these polygons and extruding them. But we don't want just to extrude them straight, because often in photonics, as you might know, or the technologies, we have sidewalls, or we have, want to model some sort of tapering of the geometry. And so what I've done is we start with these polygons again. So here I'm just going to show the same polygon as before. Actually, well, yeah, it's this one that I just showed you. I'm not going to render it again. The difference here is that we now have a prism object. So that's the other addition from Meshwell. The prism object takes the polygons like before. It takes the model you have to assign it to, of course, and also a name. But it also takes this argument called the buffer. And what the buffer does is just a hash map. And the keys are z positions, and the values are buffer operations. Because in general, if you have a polygon in the plane, you don't know how it's oriented. So it doesn't really make sense to say, grow in X or grow in Y. So what we do is we grow it uniformly or shrink it uniformly. And this is a way we can create sidewalls in our geometry. For instance, if you take your polygon and you grow it at the base and shrink it at the top, then you get a sidewall. And so we add this buffer. We do the same kind of call as before. We have some meshing code. And here I have some code to use Plotly to look at it in 3D. And you can see it's not the best. I had to do this so it could render in the browser for the docs. But yeah, you can see that this is the same X we had before, except now I'm also extruding it in 3D. And I had a buffer that looked like grow at z equals 0. I want you to grow by 0.05 units of length of my model, and at z equals 1, you have to shrink. And so if you squint really hard, you can see it. You can see the sidewall. So that's polygons, that's prisms. That's still pretty lame. What we're really interested in is how to combine a lot of these things together seamlessly without having to fight with GMesh. And so that's really the power of this library. That's what we use the most, what I've been using the most over the last 2 years to do open source simulations, is these multi-entity models with an easy, simple API. And so we'll do our imports again. Here I'm going to create the same polygons as before, right? I have my box with the X from the lines. I'm going to add crazier shapes like this S. This S curve is just a string that follows a path, and I extrude it. I buffer it. And I'm going to do the same kind of calls where I create a model, the Meshwell model that tracks some stuff. I'm going to create my polysurface for the first polygon, the second polygon, and we can also use native GMesh entities. So I have this other object that you can just give it a GMesh function with some arguments and then some other parameters. As you can see, there is this new argument here called mesh order. I'm going to explain that quickly. That's the key to all this. We put all these in a list and we throw them in the mesh, and let's see what we get. All right. So already looks more complicated. Right, so a few things. So we have the X shape we had from before. I added this other polygon that was this S, and then I buffered it, so that's what we see here. And then the GMesh circle and the GMesh rectangle. So first thing to notice is that everything is colored according to their name. So when I created the GMesh objects, I gave them a physical name, and they get tagged appropriately in the mesh. Nothing is overlapping because of this concept of the mesh order. So things that have a higher mesh order, they take priority. And so that's why you see this X polygon comes first, then we have the S, and then things just get cut out if they have to. And then all the interfaces between the different combinations of objects also get assigned. If I zoom in here, you can see I have in teal, I have my first polygon, in red I have my disk, and then at the interface of the disk and the polygon, that's this red line, it's labeled as the name of the first thing. There's some delimiter you can set, and then the name of the second thing. Same thing at the here the red interfaces with nothing, so you get the disk with nothing, and so on. So that's very handy. If you want to change the order of priority, you can, and also you can also that's what I just tried, but I can also filter this plot by specific physical names. And so it's nice to see that things get labeled appropriately. So if we change the mesh order here, I'm just reverting some of this order. We can see that we'll get a different looking, here I'm also playing the wireframe just for fun. But now you can see that this middle, actually, let me not plot the wireframe, it's fine to see. Now if we compare to before, right, now the X has lower mesh order, and so it gets overridden by the other shapes. There's also other flags in these entities. For instance, there's a mesh Boolean flag that says whether you actually mesh this thing or not. So if I run what this should look like, here I set everything's the same except the disk and the S. I decided to set the mesh Boolean to false, and so now they still show up in the sense that if they have a higher mesh order than something else, they will override. That's why this X gets eaten up by the S here, and the interface also gets named, the S with the polygon, but the S itself is not there. And there's lots of situations where you might want to do that for a simulation. For instance, if you're modeling metals in an RF system, usually you just need the surface of the metal. You don't need the whole interior. So that's one way to have metal regions in your mesh on which you only represent the surface. All right, so we're about halfway through and we're doing good on time. The next thing you might be interested in, so I've been talking a lot about CAD, but not so much about the mesh itself. So the most important thing when you do these kinds of meshes is to find a way to parameterize the actual nodes around geometries, because you want the triangles or the tetrahedras you're using for your simulation to be very well proportioned. If they're very long and thin, then your matrices are usually very ill-conditioned, then you'll see your solvers crash. So the way to do that, there's a way to specify resolutions when you define these Meshwell objects. The first thing you can do, let me create some common objects here. When you actually call the meshing command, there is a flag called default characteristic length, and that's basically the base mesh size you will get everywhere if you don't set anything. So here I'm going to sweep that number from 10 to 1 to 0.3, and we'll look at the output. So the first mesh, this one has, let me just finish things, see what happens. So here, if I set the default characteristic length to 10, that's a length scale that's basically bigger than anything in my model. And so I get these very ill-shaped triangles, but the thing still meshes. If I set it to 1, now you can see that the characteristic distance between different nodes becomes about 1. It's never going to be exactly 1 because this meshing is an optimization problem, but it's already looking a lot better. And finally, if I do 0.3, then it's even finer. So that's useful. But usually you don't want the same resolution across your entire domain because the physics is going to be confined to regions of interest, right? If we're doing integrated photonics, for instance, light is usually trapped in a waveguide, and so far from the waveguide, you don't really care. And so there's a way to have more control over the resolution you get. These polysurfaces or prisms or GMSH entities that I've presented, you can give them a list of, I call them resolution specs. And the first resolution spec, the simplest one, is the constant resolution field, which you just give it a number, which is this characteristic distance between nodes, and you say what to apply it to. Is it the surface, the volume, the surface, or the lines of the object? So here, what I'm going to do is I'm going to apply the constant field. So on this box, the magenta box, I'm going to apply a constant field inside. And on the outer box here, I'm going to apply a field on the interface. So let's run that. And so you can see that this, let's go back to the actually. So I didn't set the, in the red box, I didn't set anything. And so I'm getting the default characteristic length, which is 2 here. So as you can see, it's about 2. In the constant box here, I set a characteristic length of 0.3, so I'm getting a much finer mesh. And at the interface, you see they do line up, even though it doesn't look very good right now. And on the teal box, I specified that I only wanted the curves of this entity to have this resolution. So the inside is still coarse, but the interface is more fine. That's okay, but as you can see at the transition between a small mesh and a large mesh, we get these really ill-shaped elements. That's going to give you a lot of trouble when you simulate. And so there's more powerful resolution specs you can use. The first one I'm going to talk about is this threshold resolution. This threshold field, what it does is it goes from a size min to a size max, and then and over some distance, it linearly interpolates the size of the elements. And again, it's a resolution spec, so you can decide to apply it to the surface or the curves of your model of your entity. So let's run that, and let's look at the output. So here I also made it so that the magenta box still has a constant resolution, because these resolutions you can give as many of them as you want to every entity, so you can have arbitrary complex combinations of resolutions. And as you can see, it looks a lot better already near the interface. Same thing here. And the problem with this threshold field is that if you transition too fast, here it's hard to see, but because it's a linear change between some size min and size max, if the size max is not the same as your background, then you're gonna have a discontinuity at the at that point, and sometimes the elements get very ill-shaped when you do that. So we also have an exponential resolution. It's a little more expensive to compute, so for big models, it doesn't work very well. But this one will give you a much smoother mesh because it creates a size field that's based on an exponential growth of your size element. So and you can parameterize it by the length scale over which there's a growth factor. So you start with a size min so here I'm saying for box 2, that's the magenta box. From its curves, on its curves, I want a size min of 0.3, but I want this size as you go away from the curve to grow a factor of 2 every 2 units of length. So let's see what it looks like. This one has a bit too many points, so it takes time to render. So it's more apparent to see here on the teal box. But it's a much smoother change in the size field. The last thing I want to talk about with the resolutions, often you don't want the same resolution depending, you want a resolution that scales with the size of the feature you're trying to represent. And so we do have a way to do that here. The way to do that is, so let me create I have the same kind of API, but there's this parameter in the size fields, in the resolution fields, that's called min-max or max-mass. Mass is just an arbitrary word that captures the length of the element if it's 1D, or the area if it's 2D, or the volume if it's 3D. And so if you can specify a min-max and a max-max for the elements in this, for instance, these sets of polygons here, and then it'll filter. So let's take a look. But here what I'm doing is I'm creating 2 boxes, one that has a area of 1, one that has an area of 2 times 2, 4. And I'm setting a constant resolution in the boxes. But also, very importantly, these 2 boxes are part of the same polygon. They're the same multi-polygon. So there's no way to distinguish them at load time. They're not different. They're not different polysurfaces in my model. They're one polysurface. But my resolution field is such that I'm only going to apply a fine resolution. So the original mesh you can do the same. If I just use a constant field, resolution 0.1, and I apply it to all the surfaces in my model, then all of them get affected. But in the second mesh that I'm making, I'm adding this max mass equals 4. So now I'm only going to get this resolution for the entities whose surfaces are smaller than 4. So that's what you're seeing here. And that's very powerful. Again, you can apply it to surface, curves, volumes. And so that allows you to target areas where you have very fine features. You can mesh differently than areas where you have large features. And that's a very powerful ability. I'm going to move on to the last. So that's pretty much it for the Meshwell part. Now I'm just going to quickly flash through what you can do with Meshwell. But I guess before we go, maybe there's questions on the actual package or GMesh. I can take them now, or we can circle back at the end. Whatever people prefer. All right, I'll keep on with the demo then. So there is a notebook in. So originally I made this because you see a lot of the things that I brought up during this presentation are things that show up a lot if you're doing integrated systems. So first of all, you're dealing with polygons, right? We use GDS. Usually foundries will accept GDS to represent polygons to be fabricated. So we needed a way to handle GDS or polygons. Sometimes you have sidewalls, right? So we have a way to extrude with a sidewall. That's also taken care of. Things will overlap a lot. You have, in photonics, for instance, you have bottom oxide, silicon, top oxide, and you want the top oxide to fully overlap with the silicon. And And so, yeah, so there was a plugin that was made at some point with GDSFactory, which is a tool I mostly used for layout back in the day. And so there's still some remnant of that plugin that I'm going to show here. There's a caveat that I haven't updated the plugin since Meshwell, an older version of Meshwell, so the API is a little different and there might be some more bugs, but it still works pretty well. So what I'm going to do here is I'm going to, load GDSFactory, defeature a little bit so the mesh is faster to run. And GDSFactory also has this concept of a layer stack. So the way GDSFactory, the meshing works is it takes the component polygons, so that's your GDS, that's you're familiar with, but it also needs a concept of what these different GDS layers map to. And the way we do that is with this layer stack. So if we go to GDSFactory code, there's a generic layer stack that I'm using for the example purposes. But it's basically these layer level objects that have a layer, and then it's supposed to represent the chip as it is when it's done being fabricated. And so you have, for every layer level, you have a quote unquote layer, and it's not a GDS layer, it's actually a combination of GDS layers. So here I printed this layer stack that I'm showing you. And as you can see, the substrate level, that's just a generic wafer layer, but something like the core of your waveguide, that's actually a combination of GDS layers, right? It's wherever you have, for instance, the core layer, and then wherever you remove some etchings. So there's something, so depending on the fab you work with, some of them will do that for you, but some foundries, you actually design, with a large block of silicon, and then you add etches. And basically this layer stack and these logical layer operations, right? They just look like, if you, so the layer core, for instance, you can actually, we can see it very well here. I haven't looked at this in a while, but oh yeah, we have it here. So yeah, so the core, for instance, there's some overloaded layer objects in GDSFactory, and you can take very simple operations. So either unions or intersections or differences. Anyway, so the layer stack, it has the layers, which gives you the polygons. After all the operations are taken, it has a Z-min, a thickness, and then a mesh order, which is the same mesh order we had in Meshwell earlier. It tells you if two things conflict, which one takes precedence. So that's what we have here. We have the stack. Here, I'm going to choose a random component from the GDSFactory library, just this heater. So it's relatively complicated. You have this core waveguide. You have a heater that's curved and a bunch of vias. So because it's an older version of Meshwell, the resolutions work a little bit differently. They assume everything's a threshold field, and they take the arguments in the dict, but I'm not going to spend too much time on that right now. And there's different, there's a function in GDSFactory, it's called getMesh in G plugins. It takes the component, it takes a string argument that tells you what type of mesh you want, because you can do 3D meshes, but you can also do cross sections in the plane or out of the plane. So here I'm going to first do a UZ cross section. So U is just a line in the plane, and Z is going out of the plane, so it's going to give you a cross-sectional cut of the geometry. We give it some bounds to take the cut from, and then there's some settings, and the stack, very importantly. So let's run that, and here I'm going to use GMesh to look at it. So let's take a look at what we did here. So we have this GDS. I chose to take a cross section. I'm going from actually I'm taking this cut here. So I'm choosing an X value that's right in the middle of this component, and I'm going from Y max, that's the minimum here, and all the way to about the middle. So the cut I'm looking at is right here. And so that's what you see here. Let me make it clear. So here we have, let's see what we expect. We have 3 waveguides, a heater, and then everything else that's on the wafer layer is going to be represented as well. That's like your background. And if we look back here, on the wafer, we have a substrate, we have a bottom oxide, and we have the cladding. So that's what we have. We have a substrate down here, a bottom oxide, cladding, and then we can see our our heater metal appear, and then the waveguides. And the waveguides, as you can see, they even have a sidewall. So it's very convenient because now I can take an arbitrary component slash GDS, and I can take an arbitrary technology stack and just get a mesh to do whatever I want with it. So that's cool. So 2D is useful for some simulations. Most of the time, you might want to do 3D, however. So to get a 3D simulations, it's just as easy. You just change the type here to 3D. This one's going to take a little more time to mesh. So we can wait. We added some, we added a progress bar because people like progress bars. Any questions so far?
Simon, while it loads, can you comment on, I don't know if you can hear me, but can you
Yeah.
comment on what kind of metadata this mesh format can support? Like
So
this box, you can name the boxes, I could see that, right? But what else?
So the gmesh.msh format, it's the physicals is the only thing, right? So you have the actual, so in the mesh file, we can probably take a look at a mesh file actually, like this one here, heater. This is the one we just did, heater UZ. It has these names for the collections of nodes that belong to different subsets of your mesh, and then it literally has the coordinates of the mesh points. That's all there is in there.
I see. So for an actual simulation, you would need to create a dedicated script for each component you want to simulate. It's not self-contained, right?
Yes and no. So the way I usually do it is this part takes care of the geometry. So it takes the component, it takes the layer stack, and it gives you the mesh. And then we usually add a little bit of, so in GDSFactory, there's a concept of, usually the thing you want to add is like boundary conditions and, sources, whatever, in your simulation. And that can actually be, you can fake it with these physical, like you can add fake layers to your stack and basically name things differently. And then they will show up in your mesh, and then you can tag them. And then your simulator software will just say, oh, if I want say you're doing an RF simulation, you want a lump port somewhere, then, I'm going to take this surface that has this specific name and call that my lump port. So you can store stuff in the mesh like that.
Understood. All right. Thank you.
Yep. All right. So it should be done. Let's take a look at our 3D mesh. So much cooler already. Let's toggle some things. It's a bit slow. I'm waiting for the visibility menu to pop. All right, there you go. Well, first of all, I'm going to just look at the 3D element faces because that's a little more interesting. Then I remove the 2D edges. And I'm going to, what's going on? Oh, I'm getting some GMesh bugs, of course. It wouldn't be a live demo without bugs. Let's open it again. Amazing. Just kill it. Well, it worked great yesterday, so open source, right?
I think it's more like memory usage on the computer.
Maybe I'm not that. It's 5 gigs out of 30. Should be fine.
I stand corrected.
Yeah. No, I mean these things come up all the time, so this is the joy of. Although to be fair, commercial software also has a lot of bugs, so it's not like you can escape it. But anyway, you kind of saw the mesh. I'll run the whole thing again just to regenerate it while I go through my last example. Let's with my component stack component, and then we'll mesh it again. Actually, I don't need to mesh it again. I have the mesh file already, but it might have deleted it. So finish. Take this heater underscore 3D. All right, so that's a new instance. That's visibility, faces, that. So now my cladding's hiding everything. So let's the visibility menu is the thing that's crashing. All right, let's make sure we have everything except the cladding. Oop. All right, much better. And so yeah, that looks a lot like the GDS. And if you maybe you didn't notice because I went by very quickly, but when I set my resolutions, I did want a finer resolution around the core and the heater than the rest, and that is what I'm getting. Cool. So that's and then I have one more quick example that I'm not going to explain in detail, but I did promise it in my abstract, so I will pay lip service to it. So this has been a presentation of ever more poorly maintained software. So Meshwell is the more well maintained. The GDSFactory plugin is a little lagging behind. This is another code that I started writing. It's also on GitHub. But this one's like very deep in I think if I look up my repos, yeah, GDSFactory. It lives on a dev branch in something. I basically open sourced this idea in my PhD and never finished cleaning it up. But the idea for this software was to take this automatic meshing from GDSFactory and take the open source simulator DEVSIM, which is for TCAD, so PN junctions, resistors, stuff like that, and have an interface between the two. And the main interest for me was, detectors, modulators, optoelectronic stuff. And so I have this notebook here that I'm going to go through where I simulate a PN junction modulator using this meshing I just talked about. So we first start with the GDS like before. So this is just a PN junction modulator. You have your core here, you have slabs, some metals, and then dopings. Is there a question? Okay. I have, again, I define a layer stack. In this layer stack, it's a little more interesting because we have, let me find if I can find it, or maybe I can't. Suppose layer stack, I think the layer stack is in, yeah, okay. Layer stack is a little bit more interesting because it has, in the doping layers, there's extra metadata for how the doping should look like. And so, yeah, we get a layer stack. Then we define the simulations a very similar way to what I showed before, some resolutions for the different layers. Here, I'm taking a cut in 2D, like the first GDSFactory example I showed. And there's some pre-processing that happens to allow us to answer the questions. I'm taking some of the ports in the GDSFactory component, using that to modify the layers where the port touches the polygon. So it allows me to add boundary conditions. And now this is the thing I'm going to completely skip for this talk, but yeah, a DEVSIM does not have any built-in physical models, so you have to put that in yourself. So here I have a bunch of settings that choose different models. So anyway, we run this, we get a lot of output text, and we get a simulation that I'm going to show to you right now. Let's take a look. So I'm using ParaView because there are, let's look at the first mesh. So let's go back to the GDS to remind ourselves what it looks like. But it was this. So I'm taking a cut of this GDS about in the middle. We expect a slab of silicon, some metals, and the core. And that's what we're seeing here. We have the metals here. There's a 3-metal layer process with vias, with the sidewalls. So everything gets captured. The mesh looks like this. And here there's already one round of refinement. I'm going to touch on that really quickly. So that's the mesh. we run that. So for these p-n junction simulations, you have a very large change in the one quantity, in this case, the doping concentration, right near the junction. And so it's very important to have a refined mesh there. Often when you use these open source solvers, you create your initial mesh the way I showed you, and then the solver itself will have a way to split edges where it has to reduce some error metric. DEVSIM doesn't have that. So here what you do is you implement your own remeshing procedure where you solve for the physics once, you look at the output, and here I had some, refinement. If you dig down here, I'm basically looking at the difference. If I have two nodes, if the quantity, say the electron concentration changes by, more than one order of magnitude between the two nodes, I say, oh, here, I want a new mesh with a refined size field. So that's what's happening. And it actually goes through a few remeshing steps. So, and the number of bisections, that's the number of edges it cuts every time, goes down over time. And at the end of this, you're left with so at the end, that'll be here. Let's take a look. Yep. So as you can see, there's a lot more mesh points right in the middle. And that does correspond where I'm going to need some logarithmic scales here. Right. So you can see where there's a large change in the electron concentration, I have a much finer mesh. So that's very useful. Once you have a mesh you're happy with, you can actually ramp the boundary condition, the voltage in this case, and look at how the electron concentration changes. You can also look at the current through the terminals, and you can see you have the expected behavior where in forward bias, you start to exponentially increase current. In reverse bias, nothing happens much. And so we get these charge densities, we get them as a function of voltage. So if I go to -5 volts, for instance, and I look at the same mesh, let's look at the edges. Let's look at the electron concentration here. Too many fields, right? You can see am I doing? Yeah. Let's just look at surface. And look at surface. So at 0 volts, I have, some depletion width. At -5 volts, it's a much larger depletion width. That's the modulation effect we're going to use here. So here, I used to use PyVista, and it broke recently, so I can't plot in the notebook. Once we have this, and we can also look here, I'm taking a 1D cut of this to see as a function of voltage, what does the electron concentration or the hole concentration vary? Then I'm going to use another solver called FEMwell. I'm using the same mesh, but here I'm solving for so you see it's the same mesh, but here I'm assigning a permittivity, so an index of refraction, and I'm solving for optical modes. So I did that. Here it's the notebook, it doesn't render well, but you can see there's a mode confined right where the waveguide is. And if I can superimpose this charge distribution on the waveguide to give me an index of refraction change from the bare silicon. And then what I do is I'm not going to go through the details, but FEMwell has a way it's a finite element solver. It has a way to, you can solve for an optical mode and then perturb it with an index perturbation to get the refractive index shift. So that's what I'm doing here. And as a function of voltage, I can see the effective refractive index shift and the absorption change as well, because the refractive index shift associated with free carriers also has a lot component to it. So anyway, that was all I had for today. Just want to talk about how this wrapper we have to make GMSH easier to use, and how we can combine it with GDSFactory and then solve physics on it. So yeah, thanks for your attention.
I want to thank you again for taking some time out of your day and leading this workshop. I think we're about at noon, but if there are any quick questions.
Thanks, Simon. Great talk. Quick question, very quick, about
Yep,
how much of this you use in production and how
a
it
lot.
correlates to experimental data.
So experimental data comes later. Well, so the heaters I showed in my old job, we exclusively use this to design micro heaters on silicon photonic chips. And once the chips came back, the match was almost perfect. But of course, the heater is a very simple problem to solve. Um, but I guess it's not just the heater, right? You also have the mold solve. So you kind of validate two things at the same time. Right now, I'm working with quantum computing, and this is more used for RF simulations. So, S parameters of gigahertz systems. And here the match, I mean, I haven't done experiments yet, but I'm matching this against commercial tools, and we can get really good agreement between, a commercial tool and an open source tool when defining meshes this way.
Cool, thank you. RF is in what's the solver for that one?
We use various solvers. I'm not going to say which ones,
Oh,
but
okay.
yeah.
Thanks.